Hi, welcome. Today we're going to be talking about the periodic table and the groups and how the fact that elements belong to a particular group can give us an idea of what their characteristics are going to be and will allow us to be able to predict or to expect certain type of chemical behavior. Alright, so first of all, let me show you and let's talk a little bit about the periodic table itself. As you remember, the columns are called groups while the horizontal rows are called periods. Now there are 8 groups that we want to worry about, or that we have numbered for you guys, and now you can see that I have simplified the numbering system in this particular periodic table so we can focus on the numbers that are more interest of us and will be of interest for us also in the IB. So we'll see that we have groups 1 through 7 plus the noble gases, which is group 0. Sometimes that group is referred to group 8, so I have put that 8 in parentheses. Group 1, with the exception of hydrogen, are called the alkali metals. Hydrogen, even though has somewhat similar behavior, it's not a metal, and therefore, of course, we're not going to refer to it as a metal. Group 2 is called the Alkaline-Earth Metals. All right. Group 3 sometimes is called the boron family. Group 4 the carbon family. Group 5 the nitrogen family, and Group 6 the oxygen families. Those are groups that are reactive, and we will look at the reactivity a little bit later. But we want to focus also on Group 7. That group is called the halogens. All right, and then we'll finish talking about Group 0 or Group 8, which is the noble gases. All right. Now, if you recall from last time, we remember that when we have this number groups, the number of valence electrons that the atoms or the elements in these groups have equals the number of the group. So elements of group 1 will have 1 valence electron, elements of group 2 will have 2, elements of group 5 will have 5 valence electrons. And so this is something important to keep in mind. We'll also remember that the transition metals right here at the center are going to have most of the time 2 valence electrons. Similarly, we will find that the inner transition metals will also have 2 valence electrons. All right? Now, today I want us to focus mostly on groups 1, 2, 7, and 0. And so I have selected those out here so we can see more specifically what are the groups that we want to talk about. You can see that in red I have given them the IB numbering system, and below you can see some of the other numbering systems that you may find in other periodic tables. Alright, we are going to one more time focus on the alkali metals, the alkaline-earth metals, the halogens, and the noble gases. But understand that the number of valence electrons is going to be very important to the way that elements react. So if we can go back to the periodic table above, we'll find that elements that have 1, 2, or 3 valence electrons tend to lose electrons and become cations, which means positive ions. Elements that have 5, 6, or 7 valence electrons will tend to gain electrons until they reach that noble gas configuration, or that filled valence shell configuration that contains 8 electrons. And so they will gain enough electrons until they reach 8. Group 4 is special because group 4, having 4 valence electrons, can either lose electrons or gain electrons to reach configuration that is isoelectronic with a noble gas. So depending on what they're reacting with, they will do that. All right, they will become positive or they will become negative. So the key thing to remember then is 3 and below, you're going to become a cation. You're going to lose electrons, and you're going to lose as many electrons until you get to the previous noble gas. If you are 5 and above, you're going to gain enough electrons until you reach a valence shell of 8. So keeping that in mind, let's go ahead and look at our first group, the alkali metals. The alkali metals, as you can see, are a group composed by lithium, sodium, potassium, rubidium, cesium, and francium. We're going to focus more on the more common ones, lithium, sodium, potassium. All right, rubidium not so often, and francium is definitely radioactive, so we will not be talking much about it. Because they all contain one valence electron. All right, it's an important piece of information. They all have one valence electron. They are going to become they will want to lose one electron and form the +1 ions. So we will see that lithium will become lithium plus, sodium will become sodium plus, potassium will become sodium plus as well, because they can lose one electron. They're so reactive that they will not be found in nature in pure form. So you always find lithium, sodium, potassium, any of the alkali metals in a reacted format. And so you have to actually use electricity to purify them and actually see the elements in their pure form. All right? They're soft metals. They tend to react with moisture in the air. They tend to react with oxygen as well. And they have relatively low melting points. They definitely have lower melting points than the elements in the same period in the alkaline earth group. All right? They tend to have a very violent reaction with water, and I think that you remember this from the lab. We didn't see lithium, but lithium reacts not as violently as some of the other alkali metals, but it will give us this product, and they release hydrogen gas. When we actually balance this equation, we'll see that we'll have to have 2 over here, a 2 over here, and a 2 over here. And this reaction is quite violent, and you have heat being released. All right? Doesn't release too much heat, so the lithium does not melt. In the case of sodium, as you may recall, sodium will react with water to also form sodium hydroxide, which is a base, and this is why we see in this particular case over here how it has become purple. The phenolphthalein, which is an indicator, becomes purple or fuchsia when in the presence of a base. When we first added the sodium, we may find that the sodium had some type of different shape, all right? But once it starts reacting, it releases so much heat that you can see over here it becomes a sphere because it has molten, it has become molten, and therefore it will take that more spherical shape as it whizzes around on top of the water and reacts. Finally, we may recall also that potassium can react, and notice that all of these equations are basically the same. Potassium can react to form potassium hydroxide, so it's also a base, and will release hydrogen gas. In the case of potassium, it is so reactive that it will in fact ignite and give off this pale lavender or pale purple flame, which is very clear indication of the presence of potassium. Okay? Now, let's look at the next group. If we look at the alkaline earth metals, they're a little bit less reactive, all right, because they have 2 electrons, so it takes a little bit more energy to get them to react, but they want to lose those 2 electrons and form the +2 ions, so they will form things such as beryllium 2+, or magnesium 2+, or also very commonly the calcium 2+ ions. All right, they are reactive. They are normally not found pure in nature, but there are some small pockets that you may find some of these elements. Again, it's because they're too reactive. They're harder and have higher melting points than the alkali metals, and their reactivity increases as you go down the group, just like the reactivity of the alkali metals. All right, we saw that lithium is less reactive than sodium, and sodium is less reactive than potassium. All right, the same pattern follows for the alkaline earth metals. Beryllium is the least reactive. Barium and radium would be the most reactive. We won't talk much about radium again because it's radioactive. In the image that you see there, we see the flame being produced by magnesium. When magnesium is burned, it gives you this bright white flame. All right, and then the alkaline earth metals will react not with cold water, but they will react with hot or boiling water. And the typical reaction that they would give you is something of this form. I'm just going to use M to represent the alkaline metal plus water. And in this particular case, they will give you similar products as before. But this time, because the magnesium will go to +2 ion, it requires 2 of the hydroxide ions. Hydroxide ion has an OH minus, 1 negative charge, so you need 2 of them to neutralize it. So if you had magnesium, it would react with 2 waters to give you magnesium hydroxide and a hydrogen. Or if you had calcium, this would also react to give you calcium hydroxide with some hydrogen. Calcium will react much more quickly than magnesium. You can put magnesium in water and just look at it, and maybe occasionally you'll see a little bubble. If it's very clean, very fresh magnesium, you will see a bubble in the surface of the metal. Magnesium, on the other hand, in hot water, will actually start reacting and fizzing quite actively. Not as much as we would see for lithium or sodium, but definitely enough to see some effervescence. Let's go ahead and look at our next group. The next group is the halogens. All right? And the halogens are an interesting group because they are very highly reactive. They're so reactive that, in fact, in nature, in pure form, they're never found in pure form. All right? And when you purify them, they don't want to be single atoms. They want to react to make what are called diatomic molecules. All right? And so you will find fluorine, chlorine, bromine, iodine, and astatine again radioactive, so we won't talk much about it, in the diatomic form. They will have 2 atoms bonded together, so they can reach that more stable configuration of having a filled valence shell, of each one having 8 valence electrons by sharing 1 electron from one atom to the other. All right, so they're very reactive. When they react with metals, they will form the -1 ion. Okay, they will also react in what is called covalent bonding, which means that they will share electrons, so they can reach that filled valence shell, with 8 electrons. All right, and the reactivity is different. Reactivity decreases as you go down the group, so only a high member is able to, a higher member in the reactivity can displace something that is further down. So what does that mean? Well, let's look at the type of reactions that they can make. That means that, for example, fluorine in its elemental form can react with a solution of calcium chloride, and I'm putting it in solution, so that means AQ. This is a gas. And when you bubble the gas through that, what you're going to get is that you're going to form calcium fluoride, and that's going to be in solution, and you're going to release bubbles of chlorine gas. All right? So fluorine is more active than chlorine, and so we can displace it. But chlorine could not displace fluorine. So if you took something from further down, if you took iodine, which is a solid, and you reacted it with the calcium chloride, no reaction would occur. All right? And that's because iodine does not have the power to displace the chlorine, so it's not more reactive. All right? One of the interesting things that we'll find about the halogens is that fluorine, they're all colorful, and fluorine has a faint pink color, while chlorine will be kind of a lime green, a yellowish green. Bromine is a bright orange, sometimes slightly brownish orange. And then iodine is intense, deep violet. All right? So there are beautiful colors that way. Finally, we'll talk about the noble gases. The noble gases, by the fact that they have a filled valence shell, they almost all have 8 valence electrons. The only exception to that is helium, and it's because it's got only 2 protons, and it's the first valence shell. The first energy level can only hold 2 electrons, so it's filled with 2 electrons. All the other ones have 8 valence electrons, except helium, which has 2 valence electrons. And that means that they have filled valence shells. Because of that, they are going to be very non-reactive. They do not want to form ions. They are found pure in nature because they do not want to make compounds. You can force krypton and xenon to make compounds, but it's very, very difficult. Helium and neon, for example, have never been made into compounds. So they, up to now, are very, very unreactive. All right? Now, based on what we've said, I would like you to try a couple of little questions. All right? If, and I'll do the first one for you, if we know that sodium makes the plus ion and the chlorine makes the negative ion, negative 1 ion, well, together you want to make a compound, and compounds are always going to be neutral. So how many sodiums and chlorines would you need to make a neutral compound? Well, you would need 1 of each. I want you to attempt to do the other 4 exercises. Notice there that I've given you oxygen. You know that oxygen has 6 valence electrons. So what ion would oxygen want to make? Give this a try. We'll see this tomorrow. All right? Thank you. Bye-bye.